Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an interesting equation with complex numbers. We have z to the fifth power equals z minus 1 to the fifth power, and we're going to be looking for all solutions, including the real ones. And if you're new to complex numbers, make sure to check out my lecture videos where I go over basics and ask a lot of questions. I also have another channel that focuses more on algebra, number theory, and trigonometry, tiny bit of geometry, and that's called Cyber Math, cyber with an S. Great, so let's go ahead and see how we can approach this problem, first from a real perspective, and then we're going to approach it from a complex perspective, which is more encompassing. Okay, so normally when you are given an equation like this, it's a polynomial, right? You can do a couple different things. You can use the binomial theorem to expand it and then simplify it and solve it. That's one way to approach it. Or you can actually do something more practical in most cases, which is getting rid of the fifth power. It's good that we have the same power on both sides, like, you can just use radicals, right? In other words, we can just fifth root of both sides, take the fifth root. What happens if you do that? Again, from a real perspective, if you do it, you're taking the fifth root, and when you take the fifth root of a fifth power, the root and the power are going to cancel out. So whenever you raise a to the fifth power and then take the fifth root, you end up with a. And in the case of even powers like 4 or 2, and you know that we don't write the 2, right? You don't just say that this is equal to a because the absolute value needs to be involved, which means if a is positive, then this is a. If a is negative, this is negative a. But in the case of odd powers like fifth power, you don't need to do that because it's odd numbers. So if the numbers are both positive, then their fifth roots are positive. Of course, again, we're talking about the real world, right? So when you do this, as soon as you do this, you're going to get something really weird. How? Get rid of the fifth powers and the fifth roots, and you're going to end up with something like z equals z minus 1. Can a number be 1 less than the same number? Not really, right? At least not in our world. So if z approaches infinity, no. We're not taking limits here. This is not a calculus class. This is not even a class, is it? I mean, it's just a YouTube channel anyways. But you get the idea. If you subtract z from both sides, you end up with 0 equals negative 1, which obviously does not make any sense at all, does it? So what is that supposed to mean? This is actually a good indication that there are no solutions. But wait a minute. Isn't this a quintic equation? Well, no. You'll see later on why it's not. But let me just tell you, this is a polynomial equation. And whatever the degree is, right? You have to have, by the fundamental theorem of algebra, you have to have that many roots. So if it's quintic, you have to have 5 complex roots. If you have a quartic, it has 4 complex roots. Wait a minute, did you say complex? Obviously, this channel is all about complex numbers, and we have to look at it from a complex angle, which means there are no real solutions, okay? But that doesn't mean there are no solutions, because we have complex solutions. And I'm going to show you at the end what those solutions are going to look like from Wolfram Alpha, which is something that you can use as a basic calculator. I don't want to call it an AI because I used to call it an AI, and it can't answer some of the questions that we can solve. And then some people said, oh, it's just an LLM, whatever you call it, doesn't matter. Machine learning, LLM, language model, whatever. It's a basic calculator, a complex calculator. It can solve this problem, which is good, right? For Wolfram Alpha, obviously. So there's a lot of different ways to look at it. And I'm going to show you all these perspectives, okay? But notice that we have found no real solutions. So this method is not going to work on this problem because there are no real solutions. Again, you would have the same thing if you had something like this. You would cube root both sides and you'll end up with the same weird scenario. But this one is kind of easy to solve because when z cubed cancels out, you end up with a quadratic, which is actually very easy to solve. As you know, there's a formula. There's a cubic formula. There's a quartic formula. But guess what? There's no quintic formula. Again, I repeat, there is no quintic formula. Anyways, I don't know why I keep repeating that. Some people are annoyed probably, or They keep saying, oh, we can solve it with radicals, blah, blah. Doesn't matter. Unfortunately, it's been proven that you cannot solve quintics in the general form thanks to Abel. And of course, Galois theory is a huge thing. Anyways, that's a different story. Let's get back to Earth. Now, how do we solve it then if there are no real solutions? Great. Let's go ahead and talk about the first method. Bear with me because the first method is a tiny bit painful. So the first method we're going to use involves the binomial theorem. What is the binomial theorem? Let me tell you. So with the case of n, you can expand something like a plus b to the power n or a minus b to the power n. In this case, we have n equals 5. So it looks like this. We have the binomial coefficients, which are the combinatorial coefficients, which is like 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Kind of like coming from Pascal's triangle. Remember that? The fifth row. So these two are the same. They're both equal to 1. These two are the same. They're both equal to 5 because 5 choose 1 is 5. And these two are basically equal to 10, and they're also equal. So our coefficients are basically 1, 5, 10, 10, 5, 1. Just memorize it at least up to the fifth row or down because you're going to see this a lot. Okay? So now this is what z minus 1 to the fifth power looks like. Also, because of the minus sign, we're going to have powers of negative 1, which is going to alternate. So it's going to look like this. Z to the fifth minus 5, z to the fourth. By the way, I don't have to write 1 because all powers are 1. And then 10 z cubed, and then minus 10 z squared, and then plus 5 z, and then minus 1. So notice the symmetry, and notice the alternating signs like plus, minus, plus, minus, plus, minus. Okay? Great. Now, what do we do next? We get rid of the z to the fifth, which tells us, uh-oh, this is not a quintic equation, so we still have hope, right? We have a quartic formula. Guess what? You don't want to know what that looks like. But if you really want to know what that looks like, go ahead and look it up on Wikipedia. There's a formula that you have to scroll to the right forever to be able to see the whole thing. It's gigantic. And imagine if there were any quintic formulas, what would that look like? You'd probably need an encyclopedia or maybe, I don't know, how many whiteboards, right, to fit it. So I'm glad we don't have one. Minus 10z to the third, and then plus 10z squared. What I'm doing is I'm basically putting everything on the left-hand side so that this term can be positive, and then minus 5z plus 1 is equal to 0. Great. So that's a quartic, and guess what? Quartics can be solved. Bad news is they're complicated. First of all, if you want to solve this problem, you'll probably either multiply both sides by something to make it good, or divide everything by 5, which is going to give you some fractions, and then you're going to do some completing the square stuff. Let me quickly show you what that's going to look like. Divide everything by 5, and you're going to get something like this. Okay, it's not super bad. The only problem is the constant, but we're going to put it on the right-hand side. Therefore, it's not going to be a problem. It's not going to be a huge problem, in other words, okay? So here's what I'm thinking. If I just go ahead and isolate these two things, and put everything else on the right-hand side, okay, now we can do the following. We can add something to both sides to make the left-hand side a perfect square. So what would that be, right? This number is important. Half of that is 10. If you square 10, you're going to get 100. So in other words, we're completing the square. So we need to add 100, but not just 100, because this is z to the fourth. And imagine you factored out a z squared. You would get z minus 20z. Yes, you would add 100, but then you would multiply by z squared, so that would be 100z squared. So I'm adding that to both sides. And that gives me the following, because this z squared is going to go up by 100, right? But everything else is unchanged. Now, what are we going to do? The left-hand side is a perfect square, z squared minus 10 squared. Beautiful. Now, the right-hand side is not a perfect square though, right? But we can manipulate it to make it a perfect square. And this is how we can do it. I'm just going to show you the method because I think the solution is going to take forever. And I don't really want to go through this unless you have the patience for a 30-minute video. I know most people don't like them. So I'm going to try to keep it short. I need to add the following to both sides and think about why that's the case. I would add 2k multiplied by z squared minus 10 plus k squared. And then, of course, I need to do the same thing on the right-hand side. So this plus this, same thing, of course, right? Now, notice that the left-hand side is still a perfect square while trying to make the right-hand side another perfect square. So lots of perfect squares. This one now is going to be z squared minus 10 plus k quantity squared. Make sense? Now we're going to put these together. So it's going to be like 98 plus 2k z squared. And then we're going to bring the z in. That's going to be a plus z. And everything else is everything else is a constant. So we're going to get a k squared. That's the only positive part. It's going to be minus 20k minus 1/5. Now here's the deal. Are you ready to hear that? The truth. This is a perfect square. This needs to be a perfect square as well, which means the delta needs to be 0 because that is a quadratic. And in order for this to be a perfect square, delta needs to be 0. But guess what? That's going to give you a cubic equation in k, because you have these numbers, right? And that's going to be for you to solve. It's going to complicate things. Trust me, it's going to take forever. But you can give it a try as an exercise, left for the reader. Sorry, don't hate me for this. But try turning this into a cubic and try to solve it. Anyways, now I'm going to proceed with the second method because I think the second method is really cool and obviously much more appropriate for this channel because this channel is all about complex numbers. Again, this channel is called aplusbi for a good reason because that's how you can write a complex number in standard form. And I have another channel called Cyber Math. Don't forget that, okay? I also have a short channel which I publish probably once a week or so. I have short videos and only once a week. So easy to follow. So what is the second method all about? Well, as you notice that all solutions are non-real, right? At least we know that. So why not put everything on the same side in a division way? So let's go ahead and divide both sides by this. And then we get 1, don't we? This is nice because we have the same power, so that allows us to make a common power like this. And you're probably thinking, okay, I can take the fifth root, and that should give me z over z minus 1 equals 1, and then I'll end up with the same thing, which doesn't make sense at all, right? No, that's not what you're going to do, because we're going to think in complex terms, not like complicated, but from a perspective of complex numbers. In the complex world, 1 can be written in so many different ways. That's called the complexification of 1. Or maybe I should write a book about it. That would be interesting. Or maybe an article, who knows, right? But here's how it goes. Thanks to Euler, we are able to represent complex numbers in the complex plane, which is also called the Argand plane. At the end, there's a D. It's not silent, as far as I know. So this is the real axis. This is the imaginary axis. And you can basically take a complex number, z, a plus bi, and express it using an angle theta. And of course, its distance from 0 is going to be the square root of a squared plus b squared, which is called its absolute value, which is also called r or modulus. Okay? So you do need two things for a complex number in order to put it in polar form. The angle and r. The modulus, the distance, and the angle. The angle is also called the argument. But how do you do that? Well, 1 is a real number, so it's going to be on the real axis. Therefore, we're going to have to go back a little bit. Let's erase all of this stuff and express 1. I could probably just erase. Express 1 on the complex plane as follows. 1 unit away from 0, and it's making a no angle with the real axis. Or you can call it a 2 pi radians or negative 2 pi radians, so on and so forth, right? Or can I call it 0? Well, you can, but you need to add 2 pi. In other words, 1 can be written as e to the power 2 pi n I. I forgot to say, any complex number can be written as r times e to the I theta. R is the modulus, theta is the angle. In this case, the angle is 2 pi n, which is a multiple of 2 pi, and the modulus is 1, so we don't write it. In other words, you can replace 1 with that. That's called the complexification of 1. So now you can replace 1 with this, and ta-da-da-da, now you can raise both sides to the power 1 over 5. And when you do that, the 5 cancels out, and you just do power 1 over 5 here, and you end up with z over z minus 1. What happens on the right-hand side? Exponentials. Thanks to Euler, we have this beautiful, beautiful exponential, which gives us something like this. And n is an integer, n can be 0, 1, 2, 3, 4, because when n is 5, you go back to the very beginning. Okay? Great. So, what are we going to do with this? Okay, so here's what we need to do. We need to replace n with possible values. Of course, n equals 0 is going to give you z equals z minus 1. Uh-oh, that case is out. That's the real case, but it doesn't exist because there are no real solutions. What happens if n is equal to 1? Let's just take a look at some cases, shall we? Because the rest you can figure out. If n is equal to 1, this is going to be e to the power 2 pi I over 5. But here's one thing I forgot to tell you. E to the I theta, thanks to Euler again, can be written as cosine theta plus I sine theta. So e to the power I times 2 pi over 5 can be written as cosine 2 pi over 5 plus I times sine 2 pi over 5. We know these values, even though I haven't memorized them. I think this one is like cosine 72, and this one is sine 72, which should be the same as cosine 18. I think they involve some square root of 6 or something. Anyways, you can look it up or you can just find it. There are many ways to do it. But the idea is this is equal to z over z minus 1. So if this is w, okay, z over z minus 1 equals w. We can solve for z here. Z equals zw minus w. Remember, our goal is to solve for z. So we're going to bring these z's together and isolate the w, factor out z, kind of like taking the inverse function. Z from here would be w over w minus 1. But what is w? This one, cosine 2 pi over 5 plus I sine 2 pi over 5. And don't worry, I'm going to show you the values. Divided by cosine 2 pi over 5 plus I sine 2 pi over 5 minus 1. And guess what? This is only one of the solutions which we found by replacing n with 1, but then you can do the 2, 3, 4. They're all going to give you something similar. Let's now go ahead and take a look at what the actual values or solutions to this equation look like. Ta-da-da-da. Here's what they look like. Obviously involves a lot of square root of 5 and nested radicals and so on and so forth. And obviously these can be simplified more. Okay? Multiply the top and bottom by 5. And you're hopefully going to simplify it a little bit more, I think, right? Hopefully. Now, let's see why we don't have any real solutions. From a graphical perspective, tada, if you graph z to the 5th and z minus 1 to the 5th, they do not intersect. There's no intersection point. Therefore, we don't have any real solutions. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and don't forget to check out CyberMath and aplusbi, and bye-bye.